Hi, my name is dr. Ahmath. Welcome to the course of multivariable calculus. In this video, we're going to continue our discussions about the infinite series, and we're going to talk about one of the most interesting and important series, which is called the harmonic series. Before we do this, let's do a little bit discussions about the convergent and divergent series. So we say a series is convergent if its sum is finite. So we are adding infinitely many numbers, and the sum is going to be finite. Some number. Finite means like 1, 2, some number. And in this case, we call the series as convergent. And when we have a chance to have a convergent series, so if you look to the series as a sequence, if you remember sequence, just the terms of a series without the summation, right? When we sum the terms of the sequence, it becomes a series. If the terms of a sequence becomes really small, so that at some point it is simply equal to 0, then we have a chance that the sum is going to be a finite number. Basically, you start from some number like a1, a2, and so on. At some point when n is huge, so this number is going to be 0.00001, and the next one is going to be simply 0, right? So really small numbers, so we don't need to take into the consideration all the infinitely many terms. It is just enough for us to take into the consideration only the first some number of the terms. And the sum of a series is going to be finite if the terms of a series becomes 0 for a small number of the n. So when we say the small, it's like more or less small, maybe like 1 million. Okay, so basically, if for a sequence of a series, an, if its limit when n goes to the infinity is equal to 0, then we have a chance that a series is becoming convergent. But, so sometimes the series is divergent, right? So it means that the sum of a series is so huge so that it's infinity. So in this case, if your sequence, like a1 and so on, an, it's convergent when n is huge, but it's not converging to the 0, but for example to the 1. Even in this case, for example, an, the limit of an when n goes to the infinity, and this is equal to the 1. What does it mean? It means that you start from some number, a1, a2, and so on. When n is huge, so that then an becoming 1. An plus 1 is also 1, and so on. So it is not 0. It means that, so we have infinitely many 1s, so that the sum is becoming infinity, right? So that is divergent. So which basically means that if I want that the series should be convergent, the sum of a series is finite, the limit of a sequence should be equal to 0. But interestingly, it is not guarantees that your series is becoming convergent. So basically, this is the necessary condition, but not sufficient. What does it mean? First of all, we need to write down a theorem. So basically, if a series an goes from 1 to the infinity is convergent, then the limit of a sequence when n goes to the infinity is equal to 0. Okay. So let's consider the sequence. 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5 plus and so on. So the series looks so nice and simple, and we can write down the series as 1 over n. N goes from 1 to the infinity, right? So if you substitute n to be equal to the 1, you will get the first term. If n is equal to the 2, you're going to get the second, and so on. So an, the general term of a series, is equal to the 1 over n. And if you would like to find the limit of the an when n goes to the infinity, it is going to be equal to the 0. So it would mean it would bring you to the wrong impression the series is convergent. But it appears no. This series, which is called the harmonic series, is divergent. And in this video, we're going to prove that the series is divergent. And the harmonic series is important because we are going to use the series, the harmonic series, later on in order to show the convergence or divergence of other series. So let's try to prove that the series is divergent. So in order to do this, I'm going to find out the general formula to find the partial sum in terms of like S2 in the power of n. Basically, I would like to find the partial sum S2, find the partial sum S4, find the partial sum S8, and so on. So let me find this. So S2, the partial sum S2, it means that the sum of the first two terms of a harmonic series is becoming 1 plus 1 over 2. So let me find the partial sum of S4. It means that I need to find the sum of the first four terms of a harmonic series. It's becoming 1 plus 1 over 2 plus 1 over 3 plus 1 over 4. So let me denote, like, look to the last two terms separately. So I'm going to write down these two terms like 1 plus 1 over 2. So this is becoming bigger than if I would just substitute 1 over 3 as 1 over 4. Right? Since 1 over 3 is bigger than this, right? So this is equal to 1 over 2. So the sum is equal to 1 over 2. And it's becoming simply 1 plus 1 over, it's becoming 2 over 2. Because I have 2 times 1 over 2. So now I would like to find the sum of S8. So if you find this, it's becoming 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5 plus 1 over 6, 1 over 7, 1 over 8, right? At the same time, I'm going to use the same trick or the same thing as before. So I would like to compare, or I would like to substitute this 1 over 3 as 1 over 4. This 1 over 5 is becoming like is going to be substituted as 1 over 8. This is also was 1 over 8. This is also was 1 over 8. Since I'm substituting the number with the smaller numbers, obviously this one is becoming bigger, right? So this is bigger than 1 plus 1 over 2 plus 1 over 4 plus 1 over 4 plus 1 over 8 plus 1 over 8 plus 1 over 8 plus 1 over 8. The reason why I wrote this is that the sum of these two terms is equal to the 1 over 2, and the sum of these four terms is equal to also 1 over 2. So that I can write this as 1 plus 3 over 2. I can do the similar trick with the partial sum of S16, and you may guess that this sum is becoming bigger than 1 plus 4 over 2, right? And so on. So in general, what you can write down is that if you would like to find the partial sum of 2 of n, so in this case, we find it 2 in the power of 4, or 2 in the power of 3, or 2 in the power of 2, or 2 in the power of 1, right? So you can write this down that this partial sum is becoming bigger than 1 plus n over 2, right? So the reason why I showed that is that, so if the partial sum, so the summation of the harmonic series is going to be equal to the limit of, or it should be like bigger, right, of this partial sum, bigger than the partial sum of 2 in the power of n, because I'm summing only some part of this when n goes to infinity. So it's becoming like limit of n goes to infinity of 1 plus, so it's bigger, 1 plus n over 2, which is equal to infinity, right? So this limit is equal to infinity. So this number is even bigger than infinity. It means that it's also infinity. And this sum is also bigger than infinity. It means that this is infinity, right? So this proves that your sum of a harmonic series is going to be infinite. So this is divergent series. So the conclusion is that this is really important series. Harmonic series is important and is divergent. So, and also the theorem tells you that the limit that the sequence is going to converge to the 0 is a necessary condition. So this must be hold that your series might be convergent. But it is not sufficient. So the limit that your sequence is converging to the 0 does not guarantee to you that your series is going to converge. So in our next lectures, we're going to do a couple of more, like we are going to write down a couple of more theorems and more analysis to figure out how to define whether the series is converging or diverging.